All right, so far we've talked about using a distributional approximation, a t-distribution, to do inference for regression, mostly about the slope. And now I'm going to show you how you could use a simulation approach to do the same kind of inference. So we're going to start with doing a confidence interval. And of course, when we're going to do a confidence interval, we're going to use the simulation method, the bootstrap. So I'm going to pick in StatKey the confidence interval for slope or correlation. And then I made up that rail trail example, so the data isn't here, so I'm going to need to upload the data. So we can see the same visualization that you saw on my slides before. I've got the relationship between the average temperature and the volume. I've got the same slope, 4.802, the same intercept, 99.6. I've got n equal 90, and I've got my R, my correlation of 0.427. So we observed this slope, but our bootstrap confidence interval is what are some other reasonable values we could have observed. So what we're going to do is we're going to click generate one sample. Oh, actually, I need to change this to a bootstrap dot plot of slope. We're going to click generate one sample, and then it's going to create a bootstrap sample. So StatKey is going to sample with replacement from my original data set. And so some points might occur more than once and some might occur not at all. So like this point out here, this cold day that had 287 people on the rail trail, that doesn't appear in my bootstrap sample, but some of these other points probably occur more than once. They're all piled up, so I can't tell which ones occur more than once. And so in this bootstrap sample, I get a slope that is similar but a little bit different, 5.378, and I put that dot on my dot plot. And I can click generate one sample, generate one sample, generate one sample many, many times, or I could be lazy and click the generate 1,000 samples button. And this would give me a distribution of reasonable slopes that I could have observed. And if I wanted to create a confidence interval, I could just click the two-tail button, and then it's going to show me where 95% of the data is in the middle. And in this case, 95% of the data is between 3.065 and 6.702. So that's very similar to the confidence interval that we found using the distributional approximation. We're 95% confident that for a 1 degree increase in the average temperature, we would expect to see about 3 to 7 more people on the rail trail. So this is using a simulation method, so we don't have to have those conditions upheld like we would if we were using a distributional approximation. And then we can also use a distributional approximation to do inference, to do a hypothesis test. So I'm going to go back to StatKey. And now, because I want to do a hypothesis test, I'm going to be looking in the randomization hypothesis tests column, and I'm going to pick the test for slope and correlation. And again, I need to upload my data. All right, I'm going to change this to be a randomization dot plot of slope. And it says my null hypothesis is that my slope is equal to 0. So we observed a true slope of 4.8, but could that have just as easily been 0? So we're going to make the world as if the null hypothesis were true. We're going to break the relationship between average temperature and volume by mixing up the values of one of those variables. So if I click generate one sample, let's see, it looks like it left the values of average temperature the same, but it mixed up the values of volume. So instead of having this day where it was 33 degrees out and 287 people, we still have 33 degrees, but we've got 339 people. So it pulled out the volume from another one of the days. And this resulted in a slightly negative slope of negative 1.649. So if there was no relationship between average temperature and volume, we might see a slope of negative 1.649. And we could do the same thing, generate one sample, and now on that 33-degree day, I've got 375 people, just randomly assigned. And I've got a slightly positive slope of 0.566, and I put that dot on the plot as well. And I could click generate one sample, or just get lazy and click the generate 1,000 samples button. And this is a randomization distribution, so it's centered around the null value, which is 0. Sometimes we saw a slightly negative slope, sometimes we saw a slightly positive slope, sometimes a little bit more positive or a little bit more negative, but most of the time right around 0. And then we could find a p-value by using the two-tail button, because this is a two-sided test. It's got beta 1 equal to 0 or beta 1 not equal to 0. And then I want to put in my observed statistic into this box here because it was a positive number. So I'm going to put in 4.802 and hit enter. And now it shows me that actually in the 1,000 times that I did this, I never got anything as extreme or more extreme than 4.802. It would be extremely rare to see something that extreme if the null hypothesis were true. And so just like we did with our distributional approximation, we can reject the null hypothesis.